Hi and welcome to video 8 on my video series on networks and graphs, and this is from Unit 4, Topic 3 of the General Math curriculum. So in this video we're going to talk about flow networks and how flow networks work and how we can maximize flow or calculate the maximum flow in a flow network is the main objective of this. So I'll split this up into two videos. And there'll be a bunch of examples in here as well, although we do generally work with just the one network in these examples. So a flow network is really important contextually because it can give you information about a whole bunch of different situations. Really common ones include pipes and water capacity, or roads and networks of roads and their capacity to carry cars. So these are actually used at the moment just in work with councils and planning of roads on a state level. Also crowd movement, you could do a really simple crowd analysis based on how many people can walk past a certain point within a minute along different exit points. You could use it for safety and evacuation procedures as well. But let's talk about some of our definitions first. So here's an example. There is a directed graph here, the top one, from A to B to C to D. You can see the arrows indicating direction. And this is called a single flow network because it has a single line. So it's a single line or single flow network. It goes from A to D. Now we have a source and we have a sink in a flow diagram as well. I've done this in purple over here. And so our source is A, the source is the start, and the sink is D. The sink is where it ends. So they're just technical terms that you'll see pop up. But they're also important to define early in the question so you know where the thing is starting and where the thing is ending. So in a capacity network, it could be where you're inputting water and where the water is coming out. On a road network, it could be a town to another town. Typically, a flow diagram will also have weightings, and you've worked with weighted graphs before in Chapter 10, and so I've added some weightings to the single line network from A to D. We've got 11, 7, and 9, as you can see here, and so they indicate the capacity, how much of something could flow through there. So if it was a water-based capacity situation, it might be 11 litres per minute, and 7 meters per minute, and 9 meters per minute. And by meters, I mean liters, of course. You can see pretty obviously on this flow network A to D that the maximum flow rate of this network is 7. So while we're going to have 11 litres flowing along this line, it's going to get backed up. This is what you would commonly call the bottleneck of the network. So the 7 is the bottleneck. If this was a road system, and you could get 11 cars through this road per minute, but only 7 cars through this road per minute, well, you can see that if we're working at full capacity, we're going to get a build-up just here at vertex B. And every minute, an additional 4 cars are going to get stuck there. And so you can see that happening on this network. And 7 is our maximum flow rate. So it's really important for analysis in a lot of different contexts. Here's a multi-line network. So what if the graph above was actually just a subgraph of a larger network? So as you can see, the graph above is this bit here. Well, this could be true as well. So this could now be a road network from A to D. And there are points along the way where the road splits or something changes, and that's point B, E, C, and F. And so they're important points. What's the maximum flow now? So we've got 3 distinct routes. Now you can see that the maximum flow of route, well, I'll call them route 1, 2, and 3. So let's go 1, 2, and 3. Now I've already done route 2. The maximum flow of route 2 is 7. The maximum flow of route 1 is 6. So we've got 11, and then 8, and then 6. So 6 is the maximum there. And the maximum flow of route 3 is 10 or 5. So for route 3 it's 5, which kind of indicates that maybe the maximum flow rate here is 18, the sum of those. So I can have 7 travelling along route 2, I can have a maximum 6 per minute travelling along route 1 and 5 per minute travelling along route 3. Now you might want to take a second now to think about why this is not actually the answer. And I'm going to talk about it in just a moment. You might even want to pause the video to have a think about this. You might also want to think about this joke, which is going to be a new feature of my videos, adding a joke in somewhere to make you laugh, probably mostly at me. These are all derived from an app on my phone. So the joke today is, how do you steal a coat? You jack it. Obvious. Anyway, so from A to D, I can travel 11, 7 and 9, or 11, 8 and 6, which gives me a maximum flow rate of what I perceive to be 6 along route 1 and 7 along route 2. But if I'm getting 6 along route 1 and 7 along route 2, that's a total of 13. But one of my feeder lines here is 11. So from A to B, I've got 11 cars a minute coming to point B and then adding to the flow along from B to D or along B, E to D. And I can't actually fill the capacity needed to maximize 7 and 6 because that requires 13 per minute. So I've got a new restriction. 11, because it's feeding 2 different routes, is going to restrict my ability to fill up the need for 7 and 6. So actually, my maximum flow along route 1 and 2 is, that's a really bad one of those, is 11. And therefore my maximum flow is 11 and 15, which is, 11 and 5, which is 16. So just take a moment there to think about how that maximum flow rate changes and how this example can be applied. Second example, multi-line network. What if the graph above was actually just a subgraph of an even larger network? So this is a kind of complex familiar question you might get. Can we increase the maximum flow with a directed edge from A to C? Now realistically, you've already done the analysis to this question. So what if we had a direct edge there? Can we increase the flow? So this 10 and 5 don't matter. So I'll go back to the route 1, 2 and 3. Although we've got a little bit of extra complexity. But route 1, 2 and 3, 1 and 2 are together, but route 3 gives me 5 still. And that's the best I can do. Now let's say that we divert as much of this 11 down route 1 as possible, which is 6. So route 1 gives me a maximum flow of 6, and now that's gone, and this 11 is now 5. There's 5 left of that 11. So if I run that 5 left down route B along this 7, that means this becomes 5, and then I get 5 running up here, leaving me a capacity of 4. So route 2 is running an additional 5. But I've got this route 4 now as well. I could run from A to C to D, so we'll call that route 4. And in route 4, along edge C to D, I've got a capacity of 4 remaining, which means if my edge A to C had an additional capacity of 4, I could maximize my network. If it had an additional capacity, so if I put a 4 here, if it had an additional capacity of 6, I would only use 4. So there's actually no use going beyond 4. And this then becomes a cost thing, because it might be a pipeline, or it might be a road. And if to build a road that has a capacity of 6 is going to cost more than a road that has a capacity of 4. So I would go, well, unless I'm going to upgrade road C to D, there's no use me building above that 4. And so therefore I get a 6, a 5, a 4, which is of course 15, and that 5 gives me a maximum capacity of 20. And doing A to C as 4 gives me that maximum capacity. Interestingly here, if I wanted to increase this again, let's say I made this 4 into a 6, and I wanted all 6 of those to flow through the 9, well, I could increase the capacity of, let's say, this 11, of this 9 to 11, or I could increase the capacity of this 6 to 8, because then there would be more of the 11 flowing down here, leaving me more space on this 9. So there's multiple options here. If you were analysing this for the local council on a road network system, it gives you those multiple options in a really obvious manner. So there we have single line, multi-line networks and maximising flow. In the next video, we're going to talk about how we can determine the maximum flow using cut diagrams. All the best.